Stephen Hawking, 1942 to 2018, was one of the most influential theoretical physicists in modern history. His work, especially concerning black holes, general relativity, and quantum mechanics, revolutionized our understanding of the universe. Although his ideas have expanded our understanding of the cosmos, he is perhaps best known for his groundbreaking contributions to the study of black holes and his discovery of Hawking radiation. 1. The early years and education. Stephen Hawking was born in Oxford, England, and studied physics at University College London. He went on to study cosmology at the University of Cambridge. During his doctoral research, he made significant contributions to understanding the nature of spacetime and general relativity. Despite being diagnosed with ALS, amyotrophic lateral sclerosis, at the age of 21, which severely limited his physical abilities, Hawking continued to work, produce groundbreaking research, and become one of the most recognizable scientists in the world. 2. The state of physics before Hawking's work. Before Hawking's work, the study of black holes was mostly theoretical. Black holes were predicted by Einstein's theory of general relativity in the early 20th century, and scientists like Carl Schwarzschild and Subrahmanyam Chandrasekhar had contributed key ideas about their formation and properties. However, there was limited understanding about what happens at the center of a black hole, the singularity, and how black holes interact with quantum mechanics. 3. Hawking's contribution to black hole physics. Hawking's primary focus was on understanding black holes, which are regions of spacetime where the gravitational pull is so strong that not even light can escape. These objects are defined by their event horizon, which marks the point of no return. Once something crosses this threshold, it cannot escape the black hole's gravitational influence. 3.1 The Penrose Singularity Theorem. Before Hawking's major contributions, physicist Roger Penrose developed a theorem in 1965, the Penrose Singularity Theorem, that described the formation of singularities in black holes. Penrose's work showed that singularities are an inevitable feature of black hole formation. This opened the door for the study of what happens at the center of black holes. In collaboration with Penrose, Hawking extended the singularity theorem. Together, they showed that black holes, under general relativity, will inevitably lead to singularities under certain conditions, a finding that has profound implications for our understanding of spacetime. 3.2 The Hawking-Penrose Theorem. Hawking extended Penrose's work to show that general relativity predicts that, under realistic conditions, singularities must exist. His work resulted in the development of the Hawking-Penrose theorem, which indicates that singularities are a natural and inevitable outcome of gravitational collapse. 4. Hawking radiation and the quantum nature of black holes. In 1974, Hawking made a revolutionary discovery that would later become known as Hawking radiation. This discovery combined general relativity and quantum mechanics in a way that no one had previously considered. 4.1 The concept of virtual particles. Hawking's insight was based on the concept of quantum fluctuations. According to quantum theory, even empty space is not truly empty but filled with pairs of virtual particles that spontaneously appear and annihilate each other. This phenomenon occurs everywhere, even near black holes. 4.2 Black holes emit radiation. Hawking showed that near the event horizon of a black hole, these virtual particles can be split apart. One particle might fall into the black hole, while the other escapes. The escaping particle would appear as radiation emitted by the black hole. Over time, this radiation would cause the black hole to lose mass and energy, leading to the possibility of the black hole eventually evaporating completely. This was a groundbreaking prediction, as it showed that black holes are not entirely black and can lose mass. 4.3 The implications of Hawking radiation. The discovery of Hawking radiation had profound implications for both quantum mechanics and general relativity. It suggested that black holes could eventually evaporate and disappear, challenging previous notions that they were permanent features of the universe. This also led to new questions about the information paradox. If a black hole can evaporate, what happens to the information about the particles that fell into it? 5. The black hole information paradox. One of the most perplexing problems arising from Hawking's discovery of black hole radiation is the black hole information paradox. According to quantum mechanics, information about the state of a particle must always be preserved. but Hawking's prediction that black holes can eventually evaporate suggests that all the information about the particles that fall into a black hole is lost when the black hole disappears. Hawking initially argued that this information was indeed lost, but later changed his stance, acknowledging that the information might be stored in a different form, possibly encoded in the radiation itself. This ongoing debate between physicists about the fate of information in black holes continues to be a central issue in modern theoretical physics. 6. The no-hair theorem and its challenges. Another important area of Hawking's research was the no-hair theorem, which states that black holes, once they settle down after formation, are characterized only by three properties: mass, charge, and angular momentum. This theorem implies that any additional information, such as the specific type of matter that formed the black hole, is lost to the black hole's singularity. However, the discovery of Hawking radiation challenged this view by suggesting that black holes could emit radiation that contained information. 7. Theoretical models and the quest for a unified theory. Hawking was deeply interested in understanding the nature of the universe as a whole, particularly the search for a unified theory of quantum gravity that would reconcile general relativity with quantum mechanics. In the 1980s, Hawking became a leading figure in the field of string theory and worked on ideas such as the no-boundary condition. 7.1 The no-boundary condition. Hawking proposed the no-boundary condition for the universe, which suggests that the universe does not have any boundary or edge in time. In this model, time behaves as a dimension that is akin to space at the Big Bang. This hypothesis challenges traditional notions of a beginning to time and suggests that the universe may have originated from a quantum fluctuation. 7.2 Hawking's work on the multiverse. Hawking also speculated about the idea of the multiverse, the possibility that our universe is just one of many universes. While this idea remains speculative, it has become an important topic in modern cosmology. 8. Legacy and impact. Hawking's work has had an enormous impact on science, philosophy, and popular culture. His ability to communicate complex ideas in an accessible way, especially through his book A Brief History of Time, brought the concepts of cosmology and black holes into the mainstream. His contributions to theoretical physics continue to inspire generations of scientists and remain pivotal to our understanding of the universe. Conclusion. Stephen Hawking's groundbreaking work on black holes, Hawking radiation, and the nature of the universe transformed the way we think about the cosmos. His contributions to general relativity, quantum mechanics, and cosmology have had a profound and lasting impact. Despite his illness, Hawking's intellectual legacy continues to shape theoretical physics, and his insights into black holes, the nature of time, and the quest for a unified theory will continue to guide research for years to come.